Welcome back to Astronomy 305, Life in the Universe. This is Dr. Churchill, going to give you another hour or so of listening to my very boring lecture, but I hope that you'll split it into parts and that it will be useful for you in helping you learn the material and get through the homeworks and the quiz questions. Don't forget to listen for the magic word that'll come along at some point in time. And excuse me, today I will be clearing my throat once in a while. I apologize. Today we're going to be talking about searching for life in the solar system. And this is actually one of my favorite lectures because I get to talk about imaging and spectroscopy and how it is we actually measure physical things about objects that can be millions of miles away to billions of light years away. So that's one of the things that we're going to be talking about today. Now, our learning goals are broken down to understand what are the environmental conditions in the universe or in the galaxy that we would find life. And so when we talk about the requirements for life, we're talking about, locations that must have fulfilled these requirements, physical locations that fulfill these requirements in order for life to have a chance to either originate or to be sustained. Okay, and so we want to know where are those places, and then we're going to talk about liquid water and how important liquid water is. So that's going to be very interesting to talk about that amazing fluid. And okay, and then we're going to talk about like what telescopes. We're going to talk about spectroscopy. We're talking about imaging and things like that, and how we measure things across space, and why we need space telescopes to do some of that work. Why we can do some of that work on the ground from ground-based telescopes. And then we're going to take a biological tour of the solar system based upon these requirements for life. We're going to look at each body in the solar system and sort of quickly just surmise whether they have, or discuss whether they have all three of these various criteria for life. Okay, so here is our first slide on the requirements for habitability. And by habitability, again, we mean environments such as on the surfaces of planets or inside of planets and atmospheres of planets, maybe in gas clouds in space, though we're going to really find that that's not very viable. Really, the surfaces of planets is one of our favorite locations for finding the requirements for habitability. And actually on some of the moons around certain planets in the solar system and perhaps in other solar systems. So our number one requirement is the elements for life. Now the elements for life basically comprise carbon, nitrogen, oxygen, phosphorus, and hydrogen. I don't know if I mentioned that already. And so as we know from our discussions, the Big Bang is responsible for creating a lot of the hydrogen and helium in the universe, and actually pretty much all of it. And for everything else on the periodic table, that came through the nuclear fusion processes in the cores of stars, similar to our sun, which is fusing hydrogen to helium right now, but will eventually fuse helium into carbon. And so carbon, nitrogen, oxygen, all these elements in the periodic table come from nuclear fusion in the cores of stars, which then subsequently high mass stars will blow themselves up and jettison those elements back out into space. And then also in the process of the explosion, generate a lot of the heavier elements on the periodic table, things that are further down the table than iron get produced in these explosions. So the whole periodic table is basically created through many of these stellar processes. So as we learned earlier, the organic molecules that life is made out of is a lot of carbon atoms required. That carbon is the element that does the bonding, and it was very strong bonds, and it could do single bonds and double bonds, and it can do up to a total of 4 bonds. So it was a very versatile element, and it really forms the basis for a lot of these organic molecules. So we call ourselves carbon-based in a sense. And there's, based upon our understanding of physical chemistry, carbon really is a hands down winner. Just like we're going to find out that when it comes to a liquid transport medium for metabolism, that water is the hands down winner. So we would expect that probabilistically most life would be carbon based. It's much like ours is. It has to be made out of the things that the universe has, which is primarily the elements are carbon, nitrogen, oxygen, which are primarily produced through this stellar nucleosynthesis. Just for fun, it turns out that for astronomers, there's hydrogen, helium, and everything else is called a metal. So we have 3 parts to the periodic table, and metals means anything that is not hydrogen, lithium and above. So sometimes you'll hear astronomers talk about metals. They don't mean metals in the normal sense. Now, the second thing that is very important for life, of course, is what would be the process of modifying energy from one form to another in order to use it for growth and sustenance. And so metabolism is a process of converting energy from one form to the other. And of course, you have to have energy input in order to have metabolism be sustained. One form of metabolism, of course, is photosynthesis, and that is basically the conversion of sunlight directly into energy through chemical processes. Of course, we talked about the 4 various types of metabolism, and photo was the word indicating energy from sunlight. Okay, so starlight is a very, very obvious source of energy. There's 100 billion stars in the galaxy, and most of these stars have planets orbiting around them, so there are little platforms on which this energy can get collected. And so starlight is definitely a very important ingredient for energy of life. We're going to find out later when we talk about the Jovian planets that there are other forms of energy input. And in fact, I'll just give you the hint now. They're called tidal forces and tidal effects, and these can actually heat planets and be a source of energy. So we'll get into that later. It turns out to be very important around the moons around Jupiter. So one thing about starlight is that the further you get away from the star, the less energy from the star you actually can collect. So on the right-hand side here of this diagram, there's 3 concentric spheres that are centered on this star, the sun, and each sphere is measured in this case in astronomical units, AU. And if you remember right, 1 AU is about 93 million miles, and it is the distance the Earth's orbit around the sun. So 1 AU, you can sort of think of that as that inner sphere is the radius of the Earth's orbit. Now, if you put something on that sphere, like a little square that is a collecting area, and you collect a certain amount of light, because the light's being emitted from that star in all directions, but you're just collecting, say, for example, what's in that little square, that's your collecting area. Now, the behavior of this light energy is such that it gets diluted as you get further away, because it's basically spreading out and becoming, the energy density is decreasing. So if you move your square to be twice as further away, let's say 2 astronomical units, which is a little bit outside the orbit of Mars in the case of the solar system, it turns out that your square only would capture 1/4 of what it would capture when it was 1 astronomical unit away. So you need 4 squares spread out in order to capture the same amount of energy. So basically, you've gone twice as far away and you collect 1/4 as much. And this is why we call this law the inverse square law. You go twice as far away, you square 2, you get 4, except that it's inverse, which means it's 1 divided by 4. So as you go further, the amount of energy you collect goes down. That's the inverse part. And it goes down with the square of the distance. So let's go to a sphere that's 3 astronomical units away. In this case, notice we need 9 collecting areas in order to collect the same amount of light as when we were at 1 AU. And so we would say that we've collected, our single square collects 1/9 as much of the light energy. And so now we've gone 3 times further, and that we're collecting less light, and we're collecting 3 squared equals 9 times less light. So inverse square law. Now, for example, if you went out to Saturn, Saturn is 10 times further away than the Earth. So Saturn would collect 1/100th as much light on its surface as the Earth does. So you can see that the energy budget for any kind of photosynthetic creature that might live at the orbit of Venus would be a lot smaller than on Earth. Okay, so the other thing is that these environments will cool down because of the energy input into them. And so in addition to having less energy available to them, they also would probably have slower metabolisms. So that's number 1, elements for life, and number 2, energy for life. And starlight is a major source of that. But again, we'll talk about other sources later in the course. Now, if you look at the third requirement, it is the transport medium for metabolism. In other words, you want to take organic molecules from one location, you want to move them to another location, or in the sense that you want to transmit the energy and you want to transmit the actual physical chemicals themselves from one place to the next. Now, there's a lot of different fluids, and the fluids exist in different environments, different temperatures and pressures. We're just going to basically concentrate on temperature. So before we go through the 4 reasons of why water is the best, let's just take a tour of these properties of water. So let's move to the right-hand side of the slide, looking at table 6.1. And on the left of the table, you have the substance, and then you have its freezing temperature, boiling temperature, and the range of temperatures over which that fluid is liquid. So starting with water, it freezes at 0 degrees. So anything below that it's a solid, as we know, what we call ice water. And anything above 100 degrees Celsius, it is in a gas form, what we call water vapor. That's a 100-degree range over which water can be liquid. Now, that's a broad range. If you think about what it feels like to be at freezing and what it feels like to be at boiling, which is 212 degrees Fahrenheit, try to put your hand in a pot of boiling water. That's a large temperature range over which this substance can actually be a liquid. And that's a positive. And the reason it's a positive is because that means you can have a large range of environments on planets or in the universe that can be cold and you still can find liquid water, or that can be quite warm and hot and still have liquid water. Okay, another candidate substance is ammonia, and then another one methane, and another one ethane. Okay, methane and ethane are just forms of oil. Let's look at ammonia. It has common elements in it, nitrogen and hydrogen, just like water has hydrogen and oxygen. But it turns out that in this case, ammonia is liquid only at very cold temperatures, minus 78 degrees. Anything below minus 78, and it is a solid, and anything above minus 33, and it's vapor, it's ammonia vapor. So that's very cold, and it's a narrower range of temperatures, 45 degrees Celsius. So that means there's a narrow range of environments in the universe, and they're going to be bloody cold ones in which ammonia will be a liquid. Let's look at methane. Minus 182, it freezes. Minus 164, it boils. This is a very narrow range of 18 degrees Celsius over which this element, or this molecule, can be liquid. So a very narrow range of environments. Ethane, not much different. Minus 183 is what it freezes at. However, it does tend to boil at a warmer temperature than methane, minus 89 degrees Celsius. It's still bloody cold. And it has a pretty good range, 94 degrees Celsius. Okay, so the number one thing you see here is that water has the broadest range over which it is, in temperature, over which it is liquid. And that's important because then it has the broadest range of astrophysical environments over which it is liquid. So that's number one on our list on the left, the broadest range of temperatures over which it's liquid, meaning the broadest range of environments. Also from our table, we can see that the temperature of water at which it's liquid is the highest by a long shot. Now, this is very important because you want to move molecules around in this liquid. Basically, temperature is a measurement of how fast all of those molecules are jostling around. If the temperature is high, they jostle around fast, and therefore materials in the fluid will be bumped around quickly and fast, and they will be moved rapidly, relatively speaking. If you put some molecule in some liquid methane at minus 180 degrees Celsius, those molecules are barely moving and barely jostling, and anything that is embedded in there, some organic molecule, is barely going to be moving around. So the metabolism of any life form would have to be extremely slow. Okay, so one could imagine life forms of very low energy, very low metabolism that use methane. But we're going to find out that there's other properties of water that would suggest methane really is not viable. So number one, broadest range of temperatures. Number two, the highest range of temperatures from 0 to 100. That is a lot hotter than these other candidate molecules. And why is being a hotter temperature where you're liquid better? Because then you can move your molecules around faster. You can have faster metabolism, which allows life to have many more possibilities and survivability. Okay, reactions proceed faster. Now let's go back to the right-hand side, and what do we have? We have a picture of an oxygen and two hydrogens bonded together as a water molecule. Now, one of the things that's happening here is that electrons that were orbiting around the hydrogens now are in shared orbits around the hydrogen and the oxygen. And the two electrons that were orbiting around the oxygen are also now all in this shared orbits with the hydrogens and the oxygen. So you have these electrons that are moving around, and that's represented by the dashed lines between the H's and the O's. Now, the electrons, they're zooming around, but because the volume around the oxygen atom is much, much bigger, they actually spend much more time hovering around the volume of the oxygen and less time hovering around the volume of the very tiny hydrogens. And so what you have here is you sort of have these bare exposed hydrogen nuclei, the two protons, one for each hydrogen, sort of sometimes not shielded by these electrons that are zooming around. And so let's say that you are a little critter and your head is positively charged and your tail or your feet are negatively charged. And let's say you're swimming upward in the diagram toward the bottom of the molecule, toward the hydrogen ends, and you're coming in head first. Your positive electrical charge of your head is going to feel the net positive exposed electrical charges of those two hydrogens, and therefore you're going to feel an electrical repulsion and be pushed away. In fact, you'll probably end up rotating so that your negatively charged feet will be attracted. And so basically there's a force there that ends up rotating you or pushing you around. Likewise, if you were to come swimming downwards on the negative part of the water molecule, the oxygen is, you would find that your head would be attracted because opposite charges attract. So your positively charged head would be attracted to the negatively charged portion of the water molecule. And so we call this difference between the electric positive end and negative end of the molecule, we call that an electric polarity. And we say that the molecule is polarized. So the molecule of water is a highly polarized molecule. And that means that if you have other polarized molecules, like I was talking about you, swimming around with a positive head and negative feet, you have a polarized body, you are going to be forced around, and the water is going to be forced around. You're going to be twisted around. You're going to be pushed around. And this causes a lot of motion and allows molecules to be dissolved into water. Okay. And this is a very, very important part of water is that it has this impetus to make molecules be mobile, to rotate them, to push them around, and it allows the molecules to be dispersed throughout the water because of this electrical polarity of the molecules. You'll notice that, for example, salt will dissolve in water because salt is a very polarized molecule. But you'll notice that oil does not dissolve into water. It separates from water. So like your ethane molecules or your methane molecules that we were talking about as other candidates, when you mix those into water, they're eventually, because those molecules don't have any polarity, okay, they basically have a neutral feel to them from whichever direction you approach them. And so the water molecules don't pay a stitch of attention to them. And these molecules, if they're lighter than the water molecules, will tend to float to the top and separate out. And that's what we see with oil. So it turns out that methane and ethane and ammonia, none of those are polarized molecules, and therefore none of them have this property of being able to dissolve other molecules and elements into them and have the ability to rotate them and push them around and have this impetus of motion within them. So number 3 is, why is water so awesome? Because it's electrically polarized, and this allows things to be pushed around and distributed equally throughout the water, or I should say dissolved in the water. That's very good because now you have nutrients everywhere within the water, which you can then, some local molecule that needs a protein can grab it, okay, because there's some nearby. It's not separated all at the top of the water, okay. The last one, number 4, has to do with this bottom diagram. And everybody knows ice floats. And the reason ice floats is because when liquid water becomes solid water, the solid freezes in such a way that the water molecules are further apart from each other than they are when they're actually in a liquid form. When they're farther apart, then there's more space between them, they're less dense, and so basically this less dense frozen water will float to the top of the liquid water. Not so with ammonia, methane, or ethane, okay? In those cases, those molecules are locked closer together when they form ice or when they're in solid form, and so basically they're going to sink. Okay, now why is it important that ice floats? Let's consider a pond. If you have a pond and it freezes, okay, the ice, if it was more dense, would form on the bottom of the pond on the ground, and so the plant life down there would freeze. It would be killed. Anything that lived off the plant life then would die, and the ecosystem would perish. But since ice forms on the surface of the lake, it basically forms a coating over the top, and down below, the water still remains, and you have a liquid transport medium externally to life forms, and the life forms themselves inside them can then also maintain their liquid water transport medium. So those are the 4 reasons that water is very special in the universe, okay? And so you have number 1, the elements for life, number 2, the energy of life, and don't forget the inverse square law, and number 3, the amazing properties, 4 properties of water as a transport medium. And the last point of this slide is that if you're going to go and look for environments out there in the galaxy, in the solar system, or in the universe, whatever the case may be, and you want to say, where am I going to find the 3 requirements of habitability? It turns out that if you just maybe limit your search to looking for water first, that's going to be enough to find those locations, because if you've got liquid water, you must have energy, because you've got to have a fairly warm environment, 0 to 100 degrees Celsius, so you have energy. And if you have water, you've got oxygen in addition to your hydrogen. If you've got oxygen, you've got carbon and nitrogen, you've got the other elements of the periodic table, so you've got the elements for life. And so it's very important that, and one of the things we're doing is sort of a cheat or a hack, if you want to call it, is we look for the water first, and then we can determine whether the other two are there. But in 99.99% of the cases, we certainly expect them to be. Okay, so now that we've talked about the three requirements for habitability, let's talk about the techniques that we use in order to try and see if we can, find liquid water and these three criteria for habitability: elements and energy. Unfortunately, we are still confined to the planet Earth, apart from the fact that, once in a while we have a few people who are orbiting around it about 160 to 200 miles above the surface, which is not very far if you think about it. You could drive that far in 2 hours to get up to this space station. I wouldn't really call it being out in space and exploring the frontier. It's just a new area that we spend a lot of time. But we also have a lot of observational telescopes up there, as we will talk about. But for the most part, humans are confined to the planet. Okay. So let's talk about the three methods that humans do have at their disposal. The first is observations from the Earth and from Earth orbit. This is basically what we would call ground-based or space-based observations. Again, I want you to think of orbital telescopes as being Earth-based, because basically, it's only 200 miles above the surface of the Earth. It's still from the Earth, folks. It's not something out in space, way out there, in the cosmos. It's right here, right around our little eggshell, floating around it. Okay. And so then the other thing we can do is we can actually send robotic spacecraft to these other worlds. So we can get close up and personal with them. And we're going to talk about the various kinds of spacecraft that we can send. We can fly by planets, we can orbit planets, and we can actually probe planets. So that's one of the things we've been doing with robots. And of course, the ultimate goal, I think, for the evolution of the human species is to, we came out of the oceans at one point in time. Now it's time to come off the cradle of the Earth and move off into the wide universe and see what we evolve into. You got to think big here. You got to think long term. We won't look human anymore. The descendants will see a star out there, and it'll be a vague, that's where we came from. In the same way we talk about how we came out of some kind of organic goop pond. It's a whole nother transition. So anyway, back to Earth, we could send humans out to explore. Now, we've done a little bit of that. The only destination that humans have ever gone to, because Earth orbit is not a destination, it's just basically a joyride around the planet. A real only destination that humans have ever been to is the moon. Now, there were many missions to the moon from 1969 to 1972. Each mission flew 3 astronauts, and one would stay around the moon. The other 2 would get in a lunar lander, and they would fly down and land on the moon and walk around. So 6 of those missions were successful at making a landing. So 12 humans have walked on the moon. Most of them are dead now, and I think within the next 5 years, all of them will have perished, because they're all quite old. Its next goal is to get back to the moon, and also the next goal is to get a human to Mars. And the problem is that Mars is 200 times further away, and that means you spend a lot more time in space and exposed to the I want to say the elements, but really to the cosmic rays and to the solar wind particles and the radiation that's out there. And so that's the dangerous part about traveling in space. But that's a different lecture and a different story. Someday maybe we'll go to space, but in the end you've got do it from Earth, send out a robot, or go there yourself. Now let's talk about doing it from Earth. When you do it from Earth, you can use one of two techniques. And in fact, when we send robots to planets, they also use techniques very similar to this. They either take pictures or else they spread the light out into a rainbow called a spectrum, and we call this process spectroscopy. So the process of imaging and the process of spectroscopy. And I'll show you some spectra in the slide after next. But first, we're going to talk about the imaging a little bit more. So with imaging, it's very, very difficult to collect these trickles of photons, light particles, from across the solar system or from across the galaxy. And in fact, a lot of light's falling on the planet Earth every night when it's on the night side. Your rooftop is collecting light. The football field at New Mexico State is collecting a lot of light. The roads collect light, but we can't harness the damn stuff. Harnessing the damn stuff is super expensive. These two telescopes that I'm showing you a picture of, these twins called the Keck twins, they each cost $150 million to build. Okay, and then the instruments on them cost millions of dollars each and take 10 years each to build. And then it costs huge amount of operation expenses to keep it pointing on the sky every night and maintaining technological health and collecting data for astronomers. So there's a great deal of money that goes into it. These photons are as precious as gold is, really, to some people. So to collect the light is expensive, and it turns out that it gets more expensive as we get better at it because we want our telescope mirrors to be as big as possible. We want as big of gathering power, light gathering power as possible. Making it as big as a football field would be preferable, but to get a football field worth of area to focus the light down into precise imaging or precise spectroscopy is prohibitively expensive and basically beyond our technological abilities today. So these telescopes that I'm showing you are 30 feet across or 10 meters in diameter. And the next generation are going to be 30 feet across or 100 meters in diameter. So almost the next step will be almost football field size. Okay. Now, the bigger the telescope is, the more light it can collect. That seems to be pretty much a no-brainer. But the amount of light that it collects, we call that the light gathering power, or LGP for short. And that goes up with the diameter squared because basically the light gathering power goes up with the area of the telescope, and the area of the telescope scales with the diameter squared. So basically, if you double the diameter of your telescope, you have 4 times as much light gathering power. Now, what you want is you want a sharp image. For example, if I had 2 dimes and I put them all the way out at the Statue of Liberty, and I said to you, hey, can you design a telescope that can resolve and see those 2 dimes as separate dimes? That is a huge technical difficulty. So the angular separation of those dimes is what we would call the resolution. If they're right next to each other and we can't see them as separate dimes, then the resolution is the width of a dime or bigger. And so the idea is that we want the angular size over which we can separate 2 objects out to be as small as possible. That would be the highest clarity, if you will. And so this clarity, which we call resolution, gets better as the size of the telescope goes up. As the diameter of the telescope goes up, and yes, I know I misspelled it, I apologize. As the diameter of the telescope goes up, the angular vision gets narrower and sharper, what we call the resolution. So basically, more light gathering power when the telescope gets bigger, and sharper vision when the telescope gets bigger. So for imaging. Now the other thing is we have the spectroscopy, which I'm going to talk about shortly as well. And this is the spreading of the light out to its rainbow of colors. And all I want to say about spectroscopy is that it is way more powerful and way more interesting than imaging. Imaging, boy, we've got a lot of pretty pictures. They are beautiful. And, you know, if you put false color on them through using filters, you can sort of get some colors on them. But in the end, they just tell you about the spatial distribution and relative brightness of things. They don't tell you anything about, oh, the chemical composition, what it's made of. They don't tell you anything about the temperature. They don't tell you anything about the densities of the gas or any of these other physical quantities like the speed at which the gas is moving around. You can learn all of that with spectroscopy. Now, doing spectroscopy is hard. It's really a cipher job. It's like, you know, super level 3 detective work in homicide. I mean, you really have to be good at looking at clues and putting things together. So if a picture might be worth 1,000 words, you've heard that over and over, but a spectrum is worth 1,000 images, and this is the truth. And hopefully, I'll demonstrate that for you. So this is a picture of the transparency of the Earth's atmosphere as a function of wavelength along the electromagnetic spectrum of light. Now, remind you, we did go through the electromagnetic spectrum before. Now, in this diagram on the left, you have the gamma rays. Those were the short wavelength or very small electric and magnetic packets that vibrate very rapidly and are super high energy. And then at a little bit lower energy are the X-rays, the longer wavelength, then the ultraviolet. And then we have the visible region of the electromagnetic spectrum, which we know of as we move across that, goes from blue to green to yellow to orange to red. The colors of the rainbow. And then we move out into the infrared, and that's lower energy still. And then beyond the infrared, we have the microwave, which we have from, you know, your cell phones use microwaves to transmit it, and then microwave ovens use microwaves. It's just basically light, but light you can't see, and then radio waves. Now, this transparency diagram is showing you very clearly that visible light is able to go from space and penetrate all the way down to the surface of the Earth. And that's why we're able to look at the sky at night with our naked eye and see the stars in visible light, and why we have telescopes on the ground that can observe visible light and do some imaging and spectroscopy using visible light. We also, from the ground, see that radio waves can penetrate all the way through the atmosphere, and therefore we have radio dishes on the ground. We've got radio dishes on New Mexico State. The very large array is right here in New Mexico, just west of Socorro. It's a very, very prominent field of astronomy. Now, it turns out that gamma rays and X-rays, for example, and ultraviolet light really do not penetrate deep into the atmosphere. And so in this case, guess what? The only way that we can actually observe the universe by collecting gamma rays that happen to come at Earth from deep space, or X-rays, or ultraviolet light, is we have to put our telescopes above the atmosphere. And so somewhere around 200 to 500 miles above us are telescopes, like, for example, on the left is the Fermi telescope, or in the X-rays is the Chandra telescope, or in the visible, ultraviolet, and infrared, we have the Hubble telescope. Now, it just so happens the Hubble telescope does ultraviolet and it does infrared, but it just also happens to do optical spectra as well, not because it needs to be in space to do optical, but in fact because it gets above the atmosphere, and the atmosphere blurs things. Now, for example, have you ever stood on a mountaintop at night, looked down at the cities, and you see that all the lights are twinkling and blinking? That's a process called scintillation. And that's because the Earth's atmosphere is turbulent, and as the light is coming toward you, some of those photons are actually knocked out on the light path and don't make it to your eye for a very brief second, off and on, off and on, off and on, and you get a twinkling effect. It's also the effect that causes the twinkling of the stars. Well, ladies and gentlemen, if you have a space telescope, you're above that atmosphere, and the stars do not twinkle. They are solid as a rock, and so you can get very good data from space. Much better than you can from Earth. And the infrared, we have this airplane that's flying at about 40,000 feet. That's NASA's SOFIA. And that plane is for astronomers to do basically some infrared astronomy without having to go all the way into space. It turns out that's a lot less expensive than building an infrared telescope. But in the other, as you go to further wavelengths to the right there, longer wavelengths, you can see we do have a space telescope for the infrared wavelengths that don't penetrate far enough, even for an airplane to fly high enough to collect them. Okay, so this is basically these different parts of the electromagnetic spectrum. And you can see that you have to use space-based astronomy to do some of these wavelengths and ground-based for others. So from the ground, to summarize, you can do visible and radio and a little bit of microwave. I didn't mention that until now, but if you look at the diagram and you look at the radio dish down there, you can see the radio window, but the very, very left end of that radio window falls under the microwaves. And so some microwaves, the longer wavelength microwaves, actually do transmit through the atmosphere very efficiently. And that's why, for example, your cell phones and a lot of the communications that we have on the Earth use these longer wavelength microwaves. So longer wave microwaves and visible and radio. Now you can do some infrared from planes, but it turns out that you've got to go to space to do gamma rays, X-rays, and ultraviolet, and far infrared and near microwave. Now, I don't need you to know the details about far infrared and near microwave. That's not the point. The point is that there are certain wavelength bands where you need to be in space. The reason is because those types of light do not transmit through the atmosphere, so you have to go above the atmosphere to collect them. So from space, you can either use, you can do some very short sounding rockets, or you can use balloons to get instruments up there and then bring the instruments back down and collect the data from them, or you can transmit the data from space using space telescopes. Now, why am I making a big deal about this electromagnetic spectrum and our viewing the universe in these different portions of the electromagnetic spectrum? And that comes out with the next slide here. Now, this is an imaging slide of the planet Venus. And so what we have here are 4 images of Venus, one that is taken in the ultraviolet, one in the visible, one in the infrared, and you'll focus on the top layer there that's in the infrared, and one in the radio. All right, so what happens is if you observe a object in different bands of the electromagnetic spectrum, you actually get to look at different parts of the object in each of those bands. In the visible, for example, you're looking at reflected light from the sun off of the upper cloud layers. Okay, so this is light that really did not come from Venus itself. It didn't really penetrate deeply into Venus and be affected by Venus's. It basically is a reflection off the clouds in the case of Venus. So that's what you're seeing if you take pictures of Venus in the visible. If you take a picture of Venus in the ultraviolet, then it turns out that the actual emission from some of these clouds themselves, where the clouds have been heated up from the sunlight and re-radiated in the ultraviolet. So now you get some information about the clouds themselves deeper below that upper layer, the visible layer of reflection. And so you can get information on the hot parts of the clouds. Now, why do I say the hot parts? Because high energy light comes from high energy objects, and low energy light comes from low energy objects or cool objects. So high energy objects emit gamma rays and X-rays and ultraviolet light. Colder, cooler objects emit low energy radio waves and microwaves. And in between, things that are quite warm but not super hot, like the Earth, let's say our sun, which is 6,000 degrees absolute temperature. It does a lot of visible light emitting. Okay. So if you look at the third image over in the infrared, and they blocked out the day side so that because it would be reflecting a lot of infrared, and we're looking at the infrared emission from the clouds. Now remember, Venus has a very powerful greenhouse effect happening, and so the heated atmosphere itself is very hot and therefore emits a lot of infrared light. And so what we're seeing here are the cloud layers that are lower down in the atmosphere that are being heated by the planet and then emitting that infrared light out through the rest of the upper cloud layers. And so that's very interesting that we can penetrate further into the atmosphere and we can see the temperature distribution of these clouds. And if we got some spectra, we can see how fast they're moving around. In the radio, we're looking at the very low energy light. In this case, this is more like a radar image. A satellite called Magellan orbited around Venus and mapped it by bouncing radio waves down onto the surface of the planet. Now remember, radio goes right through the atmosphere and then it bounces up. And where it bounces up and very directly returns that light, those surfaces are smooth. So the bright areas are smooth. And where the light gets scattered when it hits the ground, those would be rough areas. And so those rough areas look darker. And so you can see we can actually measure something about the topography of the planet Venus by mapping it in radio. So every band has its little niche of giving something very cool. Now, this is just Venus. We could do this with any planet. We could also do it with galaxies. We can do it with black holes. We can look in the different bands and learn all kinds of different things and dissect them, their parts based upon which parts are hot, which parts are not hot, and all that kind of stuff. But let's move on next to the spectroscopy. Okay, now we're going to talk about spectroscopy a little bit. Spectroscopy turns out to be extremely powerful, so it's one of my favorite things because it's what I do for a living. I look at the spectra of quasars and study all the interesting things about them, like their chemical compositions and the rate at which they're rotating and all these things like that. So you can see in the left-hand image there, we have a white light beam going into a prism, and then it spreads out into its constituent colors, or basically the light of different wavelengths exits at different angles, and you get this thing spread out into a rainbow. This is the same phenomenon as sunlight coming down and hitting water vapor in the atmosphere, and then the little water droplets cause this effect, and then you see a rainbow in the sky. It's really a beautiful artifact of this process called diffraction. So the bottom line is that this was discovered by Isaac Newton basically while he was self-isolating during the plague in the 1660s. And so we can use the information in relative brightness in each of these wavelengths to understand what's going on with the matter, in other words, the chemical elements and the gases and fluids that interact with the light or generate the light. On the right-hand side, I'm showing you the special thing about the interaction of light with matter that allows us to decode what chemical elements are, say, in a star or in a galaxy or in the atmosphere of a planet that's on the other side of the galaxy. So it turns out that because of the behavior of the way electrons orbit around atoms, that the electric charges of the electrons that interact with the electric charges of the light particles. And because of the structure of the way the electron is allowed to orbit around the different atoms, they all interact with different energy light. Now, this causes each element to have its own spectral fingerprint, or spectroscopic fingerprint, if you will. So what we're showing in this right-hand diagram is, if you go to the top, you're seeing, say, the fingerprint for hydrogen. Now, just for reference, they're showing this sort of dim rainbow in the background. That's just so you have an idea of the different wavelengths and the colors that correspond to those wavelengths as you go from short wavelength blue light on the left to longer wavelength red light And this is just in the visible band. Now, the bright lines that you're seeing, those are the wavelengths, exact particular wavelengths at which the electrons and hydrogen will interact with light. They only interact with that particular wavelength. And in the red there, and they also tend to only interact with another one over in the blue there. And so hydrogen has this fingerprint of having these two very strong interactions, I should say, two strong fingerprints or spectroscopic emission lines in the spectrum of hydrogen. So, for example, another thing that can happen is that light can be absorbed by the atom. So, in fact, you could have a rainbow of light coming at you, and you'll be missing those two small bands of light. And that would tell you that hydrogen had removed some of those photons from the light path toward you, and therefore you knew that hydrogen was in that gas between you and the background source. Helium has a very bright line in the yellow, as you can see, and some other lines. Lithium, a bright green, a bright yellow, some in the red. Oxygen has multiple lines, has a very complex fingerprint. Carbon, also a much more complex, and nitrogen, a very complex fingerprint. And this really is basically a way that if a gas is hot, then you can see these lines in emission. And if the gas is cooler, then and there's light that's being passed through the gas toward you, you can see them in absorption. And so we're going to be talking about some absorption lines here shortly to help us understand the chemical composition of some atmospheres. Now, this is a series of spectra of planet Venus on the top, Earth, and then on the bottom, the planet of Mars. And these were taken from a spacecraft that was on its way out of the solar system, and it looked back, it took a spectrum of each of these planets so we could see what their chemical composition of their atmospheres was. Now let's go down to the big image on the bottom, if you will. You can see the color band across the bottom. That is the spectrum showing you where the visible light is, and then to the right you see it's all infrared light. And in that band you see some missing absorption lines that would be due to certain elements that are in the gas of whatever spectrum we're taking, object we're taking a spectrum of. Now, the thing about that is in the blue curve that you see in the plot above the spectral band, that is the intensity or the brightness of the light at each of those wavelengths. The dashed line there is what the sun spectrum would look like if it was very smooth. And so that is if the sun was a perfect radiator, it would have this very smooth spectrum. Now, what the solid line is in the visible light here, the optical light, the blue, red, and the green, would be what the spectrum of a planet looked like due to the reflection of the sunlight. So some of the light gets reflected, mostly in the red, but not all of the light gets reflected, and so you don't see the entire intensity of the solar spectrum coming back at you reflected off the planet. Okay, but what we're going to do is we're going to concentrate on a spectrum of the planet itself that's in the infrared. Now, if you notice in the infrared, so over on the right you have the infrared light being emitted by the planet itself. So if we look at the little square that is got the red outline around it, you can see this is the area of the spectrum of a planet that is highlighted in the box above. This is an infrared emission that's from the temperature of the planet itself. And for example, you might see some absorption out of that spectrum, that spectral shape, and that absorption would be due to some of the chemicals that are in the atmosphere of the planet. So as far as the length of the size of the electromagnetic packets, the wavelength, these are measured in microns, which is a billionth of a meter in size. So 1 micron is 1 billionth of a meter. I'm sorry. 1 millionth, sorry, of a meter. And so We're looking at a region where the wavelengths are between 8 and about 20 microns or millionths of a meter in size as far as the packets of electric and magnetic energy. Now let's look at Venus at the top. What you see is the spectrum as a function of wavelength, and then you see light that's missing at around 15 microns. This light that's missing is due to absorption of light coming from the atmosphere from carbon dioxide atoms. So the carbon dioxide atoms tend to absorb this very narrow region. That's the fingerprint of the carbon dioxide molecule, if you will. And so you see that the carbon dioxide is a very, very strong contribution to the chemical composition of Venus. There's a very strong absorption line. You don't see any water vapor, you don't see any ozone or any of these other absorption lines. But if you go down to the Earth's one, the blue one in the middle there, you see the strong carbon dioxide line. And you also see another absorption area due to ozone, which is a nice thin layer of oxygen 3 molecules that actually is very good at blocking ultraviolet light. So you can see that we see ozone in the Earth's atmosphere, but we don't see that in Venus's atmosphere. And then, of course, we see a little absorption band due to water down there around 8 microns. So interestingly, you see water vapor, ozone, and carbon dioxide in Earth's atmosphere. If you look at Mars again, what do you see? You see basically carbon dioxide because its atmosphere is primarily carbon dioxide. And it turns out if you have really, really good data, you can see a trace of water vapor. It's not completely devoid. Okay, so this is a very powerful method, spectroscopy, by which if we know the codes of the different molecules and atoms, their fingerprints, spectral fingerprints, we can then measure their relative abundances of these elements in the atmospheres. And in this case, we're able to tell, in fact, that Earth has carbon dioxide and water vapor, and that's really great. Now, the movie video that is going to be shown for this slide section is going to be about an experiment in which they turned a satellite, I think it was the Galileo satellite, back onto Earth and measured to see whether Earth would have a spectrum that would suggest that there was life. And so this is an experiment that was run by Carl Sagan. And this experiment definitely showed that there was some elements that were out of equilibrium on the Earth that would really, for them to be out of equilibrium, could only be so because of something on the planet like life. So it was effectively a way of detecting the presence of life on Earth just using spectra from space. The video is called The First Detection of Life in the Universe, and it's basically of the Earth. It's about a 10-minute video, and you definitely must watch that. It's very instructive and very helpful. Now, one of the other things you can do is you can explore the solar system by doing something called monitoring, long-term monitoring. Now, monitoring you can do from both the Earth and from space. When I say from the Earth, I mean even the Hubble Space Telescope is from the Earth. From space, I mean by sending robotic spacecraft to orbit around those other planets. In this case, what I'm showing here are 3 images of Neptune showing its long-term monitoring with the Hubble Space Telescope. There's an image from 1996, an image from 1998, and one from 2002. And this really is showing some climatic variation as the seasons change during Neptune. Now, you need to understand that since we've had telescopes trained on Neptune that are of high enough power to see the seeing disk, and that's what we call it, the seeing disk, the disk of the planet, is that we haven't seen Neptune go through a whole season yet. I think it takes 248 years for it to orbit the planet. So we haven't even seen a full orbit of Neptune since I think it's since we've had telescopes that can look at it in this kind of detail. So we never seen the weather pattern before. We never seen how it changes from spring to autumn or summer to autumn. So anyhow, this is one of the things that we can do with time. And for example, study weather patterns, climatic changes, seasonal changes. On Mars, we study dust storms. On Jupiter, we see that the red spot has been decreasing over the last 300 years. There's changes in geology of the moons. So the patterns of rings change. All these things tell us about the physics and the longevity of these things. For example, we don't know how long Saturn has had its rings, whether it formed with Saturn or later than that by some kind of moon that got too close and got crushed, or mini moons of that nature. So there's a lot of theories on that, and then we have to do time monitoring to understand how stable they are, to understand, say, how long they could have lived, or how long it was before they formed. Have they relaxed into their steady state? Are they decaying away with time? Things we want to learn about the universe. Okay, so long-term monitoring is one of the things we could do, and this is an example of that from the ground, or basically from Earth, I should say. And but the next thing we can do is we can send robotic spacecraft out, and so we can send robotic spacecraft out to the planets. And this diagram on the right is showing you our earliest attempts at that. We had two spacecraft, one called Voyager and one called Voyager 2. They left the Earth in the late 1970s and made their way out through the solar system. And say, I guess we passed by Jupiter in 1979 and by Saturn in 1981. And Uranus in 86 and Neptune in 89. Since then, that has been traveling outside of the solar system, and Voyager 1 and Voyager 2 are the farthest spacecrafts from the solar system that we have. In fact, they've exited something called the heliopause, which is the region around the sun that's the sun's influence. And beyond it is the true medium of the interstellar medium beyond Earth. So this spacecraft, Voyager 1 and Voyager 2 spacecrafts, were flybys. And a flyby basically means that exactly what it looks like. And you can come at the planet and fall into its gravity field and be slingshotted past the planet and gain some energy, therefore being able to go further from the sun and go to the next planet, be slingshotted out to the next planet, be slingshotted. And so that's what they did with the Voyager spacecraft. And now they've been slingshotted out of the solar system. It was really a fantastic time. We'd never sent anything out to those planets by that time. Voyager 2 discovered many things, rings around Jupiter, which when I was in grade school, it didn't have rings, but now, of course, everybody knows about the rings. We discovered the first active volcano around Io. We discovered rings around Uranus and rings around Neptune as well. We were able to understand the physics behind Saturn's rings for the first time. We were able to measure magnetic fields around the planets. We didn't know any of this stuff. So it's very spectacular what we can do when we go out there. Of course, the next type is the orbiter. Orbiter is exactly what it sounds like. You send it out there, you fire your rockets, or you use aerobraking of the atmosphere to slow it down. And then from that point on, you get captured by the planet, you go into orbit of it, you park in orbit, and you turn all your cameras and stuff down on the planet and your spectrographs, and you turn on your magnetometers and you study the magnetic field and how it changes and varies with time, and you can dissect the heck out of a planet. In fact, you can even try to fly by the moons and study the moons that are orbiting that planet. The next thing you can do is a lander or a probe. And so we've had many landers on Mars, for example, and that brings me to the magic word or the magic phrase, which is Mars has more cowbell. In the next few slides, you'll see why. So we have many landers that have gone onto Mars, and they're actually rovers. And we've actually sent some probes down to Venus. We've sent some probes down to into Jupiter. We've sent some probes down into Saturn and into some Saturn's moons. We haven't done that much. There's been a lot of great plans, but we haven't really had the funding to do it. The government doesn't seem to think that there's seems to think there's other things that are worth spending the money on. And finally, we have the sample return mission. So, as far as I know, we've only done one sample return mission. It was to a comet. We'll talk about it briefly. I know that the Chinese are planning a lunar sample return um, from their Chang'e 5 mission. And I guess I misspoke because we have brought back moon rocks from the astronauts, but I was thinking in terms of robotic spacecraft. We've only had one that has gone out and scooped up something and then brought it back to Earth. Okay. So this particular satellite I'm going to talk about briefly is one of the most spectacular missions that we've ever done. It is called the Cassini mission, and it launched in 1997 and entered orbit in 2004. And only recently, as 2018 or 19, I can't remember which, the mission ended, and it did so by the mission planners let Cassini fall into the atmosphere of Venus and burn up. And the reason they did that was because there could have been microbes on the satellite left over from human contact with it, and the fact that when it was built in the clean room, it wasn't perfect. You could have microbes on it, and the idea was that they would be killed and it would be sterilized, and we wouldn't have an artifact out there that would have some life on it. You know, Cassini performed multiple missions. In the bottom there, you can see color-coded orbits. These are various missions: the orange mission, the green mission, the purple mission, the white mission. I'm not going to go through each of those missions, but it's just to let you know that they dissected the heck out of Saturn and its environment, and many of those larger orbits is because they went out to the moons multiple times to take images in spectroscopy and measure magnetic fields and do things like that. And one of the things that Cassini is very famous for is discovering that there were methane oceans on the moon Titan. And so this is truly liquid fluid on the surface of another body in the solar system, large oceans of methane and lakes, much bigger than, say, the Great Lakes in the United States. They also found another moon had geysers or volcanoes of water, and this is called Enceladus, and it's a very fantastic um, um, series of movies. So I've got some links here to some movies, the introduction to Cassini and the interview and the short report on Enceladus that I'm going to put on the module link for you to look at, as well as I think I'll give you a short movie of the final mission of the plunge of Cassini into Saturn. So, needless to say, this was one of the most fantastic missions. We really learned a great deal about Saturn. So, as far as robotic spacecraft that have been probes that have gone into the gas giants, one of the major ones was the Galileo probe that went into the atmosphere of Jupiter. I'm showing you a little bit of its data down at the bottom. So if you know how to read those data, you can extract all kinds of amazing information. But as it fell through the atmosphere, it collected temperature, wind speeds, pressures, compositions, and radiation levels. And it did this as a function of depth for about an hour. And then, of course, it got too dense and too hot, and it burned up in the atmosphere. So everything that we know about Jupiter's atmosphere as a function of depth came from Galileo. And then, of course, we have a new satellite orbiting, which don't have an image for or slide about, but it's called Juno. Has been taking beautiful pictures of Jupiter. As far as Venus goes, the Cassini spacecraft was carried a probe called the Huygens probe that landed on the moon Titan. And Titan has a very thick atmosphere, mostly of methane. And as it went down, of course, it collected all this information, but it also was able to take photographs of the lakes of methane and learn a great deal about the surface. So we know a great deal about Titan, the moon, the large moon around Saturn as well. Now here comes Mars. Mars has had many robotic spacecraft on it. Viking was one of the first. There were two of them, Phoenix, Opportunity, Pathfinder, Curiosity, just to name a few of them. On the bottom, we have a map of Mars showing longitude east-west, left to right, and latitude north-south in degrees up and down. And along the equator, you can see that, for example, right smack in the middle of this map is where Opportunity landed. Opportunity is shown in the upper right-hand corner of this slide. A couple of things I want to talk about real quickly about Mars is that the first two landers were Viking 1 and Viking 2, and we sent Viking 1 to land on July 4th of 1976, the 200-year birthday of the United States, and then shortly after Viking 2 landed. So those were the first two, and then since then we've have many other probes, and we've done a great deal of surveying of Mars. It's probably the most closely studied planet of any of them. I want to mention that you can see over on the left-hand side of the map is Olympus Mons. It is a gigantic volcano, the largest in the solar system. Its base is about the size of the state of Oregon. And then you see the Tharsis volcano chain. That's a whole Tharsis bulge. And why I'm bringing that up is because, well, our next unit's going to be on Mars. And it's interesting that volcanoes mean geological activity. But today, guess what? Mars is pretty much geologically dead. But you can see that at one point it was not. And that was my point at this stage. And we'll talk about that in the next lecture. Okay. Here are a few images that come from some of these probes. I just wanted to show them for fun so you could see that there's these well thought out plans and paths that these probes take, and examining various craters and looking into them, taking images, taking soil samples and examining them. Interestingly, there's a lot of evidence for water on Mars, not present day, but definitely in the past. And in fact, there is some evidence for present day that's indirect that we'll talk about as well when we talk about Mars. So before we embark on our tour of the solar system for finding sites of habitability, I just want to talk to you quickly about the Stardust mission, which returned some particles from the comet 81P-/Wild. You can see a picture of the approach image of the comet. Of course, it was far enough from the sun that it wasn't yet heated up or didn't have a cometary tail. Down in the left, you can see the orbit of the comet relative to the orbit of the Earth, and you can see the path that the spacecraft Stardust took. And you can also see in the very lower left corner the encounter part of the orbit. And at that point in time, the orbits matched well enough that Stardust was able to come down, make a touchdown on 81P Wild, and grab some of the particles of dust, and a lot of organic molecules and a lot of water ice that are contained in these particles. And so under controlled laboratory conditions, you can see some of these particles here. And of course, then they shine light on them, they take their spectra, and they learn about all the chemical compositions without contaminating them. So that was a Japanese mission, Stardust, and that was our pretty much our first time we'd visited a comet this closely and actually touched it. And also, before we took our tour, I wanted to talk briefly about the New Horizons mission. This was a flyby mission that took 10 years to make its way out to Pluto, and it gave us our very first images of Pluto, so we'd never had any close-ups of Pluto during my entire lifetime. It only happened in the last couple years that New Horizons provided these data for us. You might notice there on the image that we have the Tombaugh region, and that's very interesting from the standpoint of New Mexico State because Clyde Tombaugh A discovered Pluto and B founded the Department of Astronomy at New Mexico State University, is also responsible for building the telescope you see on A Mountain, which may seem like an old dilapidated building at this point in time, but actually that was one of the most productive telescopes in the continental United States from the 60s through the 70s for studying the planets like Jupiter and Saturn. It has quite a very rich history if you hadn't known that from before. So New Horizons now has moved beyond Pluto and it's moved into this area that's sort of a extended belt of objects called the Kuiper Belt or Kuiper Belt, depending on how you like to pronounce it. Now the Kuiper Belt was only discovered in the last 15 years, and in that Kuiper Belt are lots of other Pluto-sized objects, if you will, other, quote, dwarf planets. And this is one of the reasons why Pluto got demoted, because in the Kuiper Belt, there's many other Pluto-like objects with their own moons. And Pluto has its own moon, has 5 moons. So we would have to keep rewriting the textbooks about every 3 months because we keep discovering new objects out there. And as I'll show you later, it turns out that when you think about it, Pluto really is not a full-fledged solar system member. It just happens to be the most inner object of the Kuiper Belt. So it's kind of a sad thing to see Pluto demoted, especially if you're from New Mexico State University. But that is the status of Pluto, and I doubt it will go back. And in the next slide, we will start our tour of the biological tour or habitability tour of the solar system. Okay, so we are going to spend most of the time talking about the terrestrial-like planets and some of the moons. After we finish our study of Mars, we're going to move on to the Jovian planets, which is to say Jupiter, Saturn, Uranus, and Neptune. Excuse me. And from there, we'll be studying the habitability of these outer planets and their moons in more detail. But today we're going to spend some time talking briefly about Mercury, Earth's moon, Venus and Mars, and then some small moons and asteroids in the inner solar system, and then briefly a touch on the Jovian planets like I mentioned. And what we're looking for here is, are there other locations in addition to Earth for which the 3 requirements of habitability have been met? And I'll give you the answer now. Only Mars meets all 3 criteria of habitability. That is, they have the chemicals for life. Earth and Mars have the chemicals for life. They have the energy required for life, and they have the water as a transport mechanism on them. Okay, so right, let's start with Mercury and Earth's moon. So what you can see here about Mercury and the Earth's moon is their relative sizes, and you can see that their surfaces, if you look at them, look fairly similar when you take a regular old black and white optical image. The thing about these bodies is that they're both quite small, and small objects tend to lose their heat more rapidly than larger bodies do. And unless you can continue to replenish that heat, the body will cool down. And that's what's happened with both of these. They've lost their internal heat. They no longer have any outgassing. They cannot sustain an atmosphere. And the reason that they lost their atmosphere, and we'll talk about this more with Mars, is that when they cooled down, they lost their magnetic fields. And you lose your magnetic field, you lose your shield against the solar wind, and it tends to eventually heat your atmosphere up and vaporize it from your planet. Okay, that's one way to say it. So they don't have any active atmosphere, and therefore they have the leftover scars because they don't have any weather, they don't have any erosion, they don't have any active geology, which also would give erosion. So you can really count the density of craters, and from there you can see that they're very old surfaces. So they're geologically dead. They're not evolving. They are frozen in time so well. And so both of these planets, or I should say moons, would probably get maybe a 1 out of 3. They both, of course, get energy from light, so they have some energy, but they don't have any internal energy. So somewhere between a 0 out of 3 and a 1 out of 3 for these two objects. Um, but let's rethink about the moon. In fact, maybe I misspoke about the moon. Mercury's still definitely a 0 out of 3 or a 1 out of 3, but the moon, I forgot, has frozen water on it. And of course, that means it probably has about 2 out of 3. So let's talk about the moon here briefly. It turns out that there's this mission that's orbiting the moon. It's called the Lunar Reconnaissance Orbiter, or LRO, and it was carrying a probe on it called the L-Cross. And the Lunar Reconnaissance Orbiter did something called neutron bombardment or gamma ray bombardment of the moon. And then if there was water or water ice in the Lagorith, it would show up as bright spots from the gamma rays. And lo and behold, in the South Pole, water ice was found. So in the upper image here from 2011, showing you these patches where this water ice was found on the southern pole. So the L-Cross probe was then sent down on a collision course at high velocity to make an impact in this basin, and the idea was to blow these and vaporize the water and send it up into space, and then everybody on Earth would train their telescopes at the moon at this exact moment and try to take spectra and images and see if they could detect the water vapor, and better than that, measure an estimate of the mass of water vapor. And it turns out that there are millions and millions of gallons of this frozen water in the moon. Now, interestingly, every project that looked at this from the Earth during the collision failed to detect the water, except for New Mexico State. They were able, through a very elaborate data reduction analysis, to use data from the Apache Point Observatory up at Sunspot by Cloudcroft, and they were able to make this measurement. So that was a claim for fame for New Mexico State to be able to do that. So basically, the moon, in a sense, has water, it has energy. It's not clear that it really has a lot of biomass, organic material from which to have life. So, the moon, 1 out of 3, 2 out of 3, whatever, but it really doesn't have all the 3 conditions for habitability. That is for darn sure. But with some intelligent human being engineering, we certainly probably could survive on the moon and harness this water ice. Going back to Mercury, sort of the 0 out of 3, 1 out of 3, we can see here that Mercury is very, very much geologically dead. It's been hit and impacted with craters. You can see the rays coming off the craters, say in the upper right. You can see the beautiful pattern of the filled-in craters in the lower left. Mercury has lost its magnetic field, or it has a very, very weak magnetic field, so that it doesn't really have any protections, lost its atmosphere. Very, very dry, very arid, no liquid water, no water ice, none of that, because its surface is 400 degrees, because it's got plenty of energy from the sun. So we're going to give it at least the 1 out of 3 for the energy for the sun, and probably not habitable in the sense that if you put some microbes on the surface, they wouldn't make it, they wouldn't survive. Now, as we go on to Venus, um, if you look at Venus, it's about 2/3 the distance from the sun, and it's about 80% of the mass of the sun, or sorry, of the Earth. And it really, if you sort of do the math of expectation, if you think, okay, well, it's kind of Earth-like, but it's a little bit closer to the sun, and you do some math, you would predict that the atmosphere would really only be, slightly warmer uh, than Earth's. And people predicted in the 30s, 40s, 50s, and whatnot that, in fact, it was a swampy planet, much like the tropical swampy areas of the planet Earth. That was, sort of 100 degrees Celsius to 35 degrees Celsius. Now, remember, 100 degrees Celsius is 200 degrees Fahrenheit, so that, that's pretty hot. But nonetheless, a hot place, but not unbearably so in terms of life, because, we know that there are extremophiles that can exist in those conditions. However, those predictions were wrong because they didn't take into account what the true behavior of the greenhouse effect was for Venus. It took Carl Sagan to do this calculation in the 60s, and he predicted that the surface was more like 870 degrees Fahrenheit. And this is way too hot for liquid water, ammonia, methane, or ethane. So you are not going to have liquid water on this planet, and therefore that ingredient, the transport medium number 3 of the criteria, is not going to be present. However, you certainly have the energy, and the atmosphere chocked with free-floating carbon dioxide, which is lots of carbon and oxygen, is all the abundance elements necessary for life. So Venus definitely gets a 2 out of 3, but without water, it really is not going to be a viable area. In other words, if we put life on Venus and that life required water, it would not survive. There's almost zero water on Venus. So I'm showing you again in the upper right the Magellan orbiter's radar map, showing you the smooth spots that are bright and the rough spots which are dark. And then, of course, some computer manipulation of the data. You can see some of the images in relief, and you can see that there are volcanoes, which indicates at one point in time Venus was geologically alive and active, and we believe it actually was covered with oceans of water. I'll give you the evidence for that in a coming lecture. But the fact of the matter is that today it is extremely arid and extremely hot. This image below the Magellan Orbiter radio map is a footprint, you can see in the lower left of the image, of the Venera 9 lander. It was a Russian spacecraft that landed on Venus. Only existed for about 20 minutes before it succumbed to the pressure and the heat. So anyhow, a planet that has become geologically inactive and had a runaway greenhouse effect. I'm going to be honest with you, we do not understand the geological history of Venus. We really are in the dark about it. There's some theories, but we really would be interested in knowing the evolution of our sister planet. Okay, biological tour of Mars. I gave it to you already. It's got a 3 out of 3. It's got the chemical elements, it's got the water, it's got the energy. Okay, so you can see in this image on the left something called seepage fractures or features. And you can see the sedimentary areas where water has piled up and then evaporated. So even though Mars looks like it's all desert, it turns out there must be water underneath the surface. And occasionally during the Martian summers, it comes out in these seepages. And so this is very interesting. We have never actually seen the water flow in these seepages, but we see from season to season, we see them appear. And then, of course, as the wind comes along and blows them away, they erode away and we lose them. But you can see clear evidence for running water. And then if you go to the lower right-hand corner, you can see these little areas that look just like riverbeds. And in fact, our probes have taken little scoops out and measured the minerals, and they have all the same little minerals that that Earth has in its riverbeds. So Mars is very much a candidate, and it could be that there's life in the underground caves. Um, and one of the things that people want to do is go to Mars and study what's going on in the caves. Um, the ice poles of Mars are made of carbon dioxide and water ice. So there's a lot of liquid and ice water on Mars. Now, when it comes to small moons and asteroids, again, these are going to be devoid of water. They're just too small. They don't have enough gravity or internal energy to drive any geology, to have magnetic fields, to have atmospheres. I think it's pretty obvious that these are basically just rocks in space. On the top, I'm showing the two moons of Mars, Phobos and Deimos, and these are way too small to sustain any of the energy for metabolism or liquid water. And then, of course, below are just some random asteroids, and as they get smaller, they're not as round anymore, but gravity tends to round things out as they get larger because it's the lowest energy configuration. So small moons and asteroids, they get a 0 out of 3. Jovian planets, I'm just going to have a single slide on these. So you have Jupiter, you have Saturn, you have Uranus and Neptune, and you can see how big Earth is relative to those Jovian planets. Now, the thing about the Jovian planets themselves is that what I'd like to share with you is that it's the moons around these planets that are really the more likely sites to find the three conditions for life. It's very true that you do have water vapor in their atmospheres. You get rain from water. You also get rain from liquid helium and liquid metallic rain coming from in Neptune and Uranus. So they're very, very active, but there's no real solid body that we've been able to probe. We don't know what the central core or the surface of these bodies are like. That's something in the future that hopefully we will learn about if we can build the technology to probe down into them. But when we come to the habitability of these planets, we'll give them about a 2 out of 3. In the sense that they really don't have liquid water in concentrations that would be required to say that they have transport medium ubiquitous on them. But they definitely have the chemical abundances, and they certainly have the energy. Okay, that does it for our lecture for C7. When we come back, we'll talk about Mars. And I hope you picked up the magic phrase. And don't forget to take the attendance quiz and click on the magic phrase. And then don't forget to watch the videos that I showed you and take the quiz. And then after you take the quiz, I would work on the homework, and everything will be due at midnight on the date that this particular module ends. And I wish you all the best, and be looking forward to hearing from you online.